What if the greatest genius of the 20th century spent the last 30 years of his life fighting a battle that most of his colleagues thought was pointless? And what if that battle turned out to be one of the most important intellectual struggles in all of human history? What if I told you that there was a theory, a beautiful and elegant theory, that said the universe is not random, that particles are not making decisions on the fly, that deep beneath the apparent chaos of the quantum world there are hidden instructions, hidden codes, hidden variables that determine everything with perfect precision? And that Albert Einstein believed in this theory so deeply that he was willing to stand alone against virtually the entire physics community to defend it? Today we are going to go on a journey, and this is not going to be a surface-level discussion. We are going to go deep. We are going to start at the very beginning, in a time when physics made perfect sense, when the universe was a giant clockwork machine ticking along with perfect predictability. And then we are going to watch that beautiful clockwork universe shatter into pieces as quantum mechanics comes along and tells us that at the smallest scales, the universe is fundamentally, irreducibly random. We are going to watch Einstein refuse to accept this. We are going to watch him fight back with some of the most brilliant arguments ever constructed in the history of science. We are going to meet the people who stood against him, the people who stood with him, and the quiet, unassuming Irish physicist who, decades later, figured out how to actually test whether Einstein was right or wrong. And we are going to follow the trail of experiments that ultimately answered the question. Experiments so important that they won the Nobel Prize in Physics in 2022. But here is what makes this story truly extraordinary. The answer is not simple. Einstein was not simply right, and he was not simply wrong. The truth is far stranger and far more beautiful than either side imagined. And by the end of this video, you will understand why. So let me ask you some questions before we begin. What if a particle does not have a definite position until you look at it? Not that you do not know where it is, but that it genuinely does not have a location until the moment of observation. What if two particles on opposite ends of the galaxy could be connected in such a way that measuring one instantly affects the other, as if they are communicating faster than light? What if the universe is not made of things, but of possibilities that only become real when someone observes them? These sound like the musings of a philosopher, or perhaps the plot of a science fiction movie. But these are the actual claims of quantum mechanics, the most successful and most precisely tested theory in the history of science. And Albert Einstein looked at these claims and said no, absolutely not. There must be something deeper. There must be hidden variables. This is the story of those hidden variables, the theory that Einstein believed was true, and what happened when science finally found a way to put it to the test. If you are someone who loves understanding the deep workings of the universe, make sure you are subscribed to this channel because we go this deep on every single video. Now let us begin at the very beginning. To understand why Einstein believed in hidden variables, you first need to understand the world he grew up in, the world of classical physics. And classical physics was, in many ways, a triumph of human reason. Starting with Isaac Newton in the late 1600s, physicists had built a framework for understanding the universe that was breathtakingly powerful. Newton showed us that the same force that makes an apple fall from a tree is the same force that keeps the moon in orbit around the Earth. He gave us 3 laws of motion and a law of gravity, and with these tools you could predict the motion of planets, the trajectories of cannonballs, the behavior of tides, and so much more. But Newton's laws were not just about prediction. They carried a deeper philosophical message, a message about the nature of reality itself. That message was determinism. In Newton's universe, if you knew the exact position and exact velocity of every single particle in the entire universe at any given moment, you could, in principle, calculate the entire future of the universe and reconstruct its entire past. Every event that will ever happen is already encoded in the present state of the universe. There is no randomness, there is no uncertainty. There is only the precise, mechanical unfolding of natural law. This idea was captured most vividly by the French mathematician Pierre-Simon Laplace, who imagined a supreme intelligence, now known as Laplace's demon, that knows the position and velocity of every particle in existence. For this intelligence, Laplace wrote, "Nothing would be uncertain, and the future, just like the past, would be present before its eyes." Think about what that means. It means that the moment the universe began, every single event that would ever happen was already determined. Every star that would form, every planet that would coalesce, every living creature that would evolve, every thought you would ever think, every decision you would ever make. All of it was baked into the initial conditions of the universe from the very first moment. The universe is not a place where things happen. It is a machine that unfolds. Now, in practice, of course, nobody could ever know the exact state of every particle. The universe contains an unimaginable number of particles, and measuring all of them with perfect precision is obviously impossible. So in practice, we use probabilities. We say there is a 70% chance of rain tomorrow, or we calculate the odds of rolling a 6 on a die. But here is the crucial point, and this is the point that will become absolutely central to our story. In classical physics, probability is always a sign of ignorance. When you roll a die and say there is a 1 in 6 chance of rolling a 3, you are not saying the die genuinely has no determined outcome. You are saying that you do not know enough about the exact force of the throw, the exact angle, the exact air resistance, the exact surface texture of the table to predict the outcome. If you had all that information, you could predict the result with perfect certainty every single time. The randomness is not in the die. It is in your lack of knowledge. This distinction between genuine randomness and apparent randomness due to ignorance is one of the most important ideas in all of science, and it is the very heart of the hidden variables debate. In classical physics, all randomness is of the second kind. It is apparent randomness. It is ignorance. There are always hidden variables, unknown factors that, if known, would make everything perfectly predictable. And this was the worldview that Albert Einstein absorbed from childhood. This was the way he understood the universe. This was the lens through which he looked at everything. And for good reason. This classical worldview was spectacularly successful. By the end of the 1800s, physics had explained an enormous range of phenomena. James Clerk Maxwell had unified electricity and magnetism into a single elegant framework. Thermodynamics had been developed into a rigorous science. The motion of planets could be predicted with extraordinary accuracy. There was a widespread feeling that physics was essentially complete, that the major laws of nature had been discovered, and all that remained was to fill in some decimal places. But there were cracks. Small, nagging cracks that most physicists thought would be easily patched up. One of these cracks involved the light emitted by hot objects. Another involved the peculiar way that light can eject electrons from metal surfaces. And a third involved the strange stability of atoms. These 3 cracks, seemingly minor, would blow the entire classical worldview wide open. The first crack was addressed by Max Planck in the year 1900. Planck was trying to explain how the energy of light emitted by a hot object is distributed across different frequencies. Classical physics predicted that a hot object should emit an infinite amount of energy at high frequencies, which was obviously absurd and became known as the ultraviolet catastrophe. Planck found that he could fix this problem by making a strange assumption. He assumed that energy is not continuous, not like a smooth flowing river, but comes in tiny discrete packets, which he called quanta. The energy of each quantum was proportional to the frequency of the light, and the constant of proportionality was a new fundamental constant that we now call Planck's constant. Planck himself was not entirely comfortable with this idea. He thought it was a mathematical trick, a convenient assumption that made the equations work, but did not necessarily reflect physical reality. But then Albert Einstein came along. In 1905, the year that would later be called his miracle year, Einstein published a paper that took Planck's idea and ran with it to an astonishing conclusion. Einstein looked at the photoelectric effect, the phenomenon in which light shining on a metal surface can eject electrons from that surface. Classical physics could not explain the details of this effect. It predicted that brighter light should eject faster electrons, but experiments showed that the speed of the ejected electrons depended not on the brightness of the light, but on its frequency. Brighter light ejected more electrons, but each individual electron had the same energy regardless of brightness. Einstein explained this by proposing that light itself comes in quanta, in tiny packets of energy that we now call photons. Each photon carries an energy proportional to its frequency. When a photon hits an electron in the metal, it transfers all its energy to that electron. If the photon's energy is high enough, the electron escapes. If not, it stays put. More photons means more electrons ejected, but each photon can only give a fixed amount of energy to each electron. It was a brilliant explanation, and it earned Einstein the Nobel Prize in 1921. But here is the deep irony that runs through this entire story. In explaining the photoelectric effect, Einstein planted one of the first seeds of quantum mechanics. The very theory he would later spend decades fighting against was partly his own creation. Einstein helped build the house of quantum mechanics, and then he refused to live in it. The quantum revolution gathered momentum through the 1920s. Niels Bohr developed a model of the atom with quantized energy levels that explained why atoms emit light at specific frequencies. Louis de Broglie proposed that not only does light behave like particles, but particles like electrons behave like waves. This wave-particle duality became one of the central mysteries of quantum mechanics. And then, in 1925 and 1926, the revolution reached its climax. In 1925, a young German physicist named Werner Heisenberg developed a completely new mathematical framework for describing quantum phenomena. His approach, called matrix mechanics, was abstract and mathematical, dispensing with visual models of atoms and instead working with arrays of numbers that obeyed specific mathematical rules. It was powerful, and it worked. But it was difficult to visualize, and many physicists found it hard to work with. Then in 1926, the Austrian physicist Erwin Schrödinger developed an alternative approach. Schrödinger's wave mechanics described quantum phenomena using a wave equation, now called the Schrödinger equation, which is much more intuitive and easier to work with. When Einstein first saw Schrödinger's equation, he was thrilled. He called it a work of true genius. Here was a quantum theory that seemed to describe a real physical wave propagating through space. Maybe, Einstein thought, this wave was the deeper reality behind quantum phenomena. But then, Max Born dropped a bombshell. In 1926, Born proposed his interpretation of Schrödinger's wave function, and it was not what anyone expected. Born said that the wave function does not describe a real physical wave. Instead, it describes probabilities. The square of the wave function at any point in space gives you the probability of finding the particle at that point. Not the density of a spread-out particle, not the intensity of a real wave, but a probability. This was a radical and disturbing proposal. It meant that quantum mechanics was not describing what a particle is doing. It was describing what a particle might do when you look at it. Before you look, the particle does not have a definite position. It has a range of possible positions, each with a certain probability, and when you measure it, when you look, the particle seems to randomly choose one of those possibilities and snap into that position. And here is the absolutely critical point, the point that would divide physics for the rest of the century. Born was not saying that we do not know where the particle is. He was saying that the particle genuinely does not have a definite position until we measure it. The randomness is not in our ignorance. The randomness is in nature itself. When Einstein read Born's interpretation, he was deeply disturbed. On December 4, 1926, he wrote a letter to Born that contains what is probably the most famous sentence in the history of physics. He wrote that quantum mechanics is very worthy of respect, but an inner voice tells him that this is not the genuine article after all. The theory delivers much, Einstein wrote, but it hardly brings us closer to the secret of the old one. And then he wrote the line that would echo through the decades. He wrote, "In any event, I am convinced that he is not playing dice. God does not play dice." That was Einstein's battle cry, and he meant it with every fiber of his being. He did not believe that the universe is fundamentally random. He believed that the apparent randomness of quantum mechanics was just like the apparent randomness of a die roll, a sign of ignorance, a sign that there are deeper variables, hidden variables, that we have not yet discovered. If we could find those hidden variables, quantum mechanics would be revealed as a statistical approximation of a deeper deterministic theory, just as thermodynamics is a statistical approximation of the deterministic motion of individual molecules. Niels Bohr, who was Einstein's great friend and greatest intellectual rival, reportedly responded to this by telling Einstein to stop telling God what to do. But let us pause here and really feel the weight of what is happening. Two of the greatest minds in human history are disagreeing not about some minor technical point, but about the fundamental nature of reality itself. Is the universe deterministic or random? Are particles real things with definite properties, or are they ghosts of possibility that only become real when observed? Is the randomness we see in quantum experiments a sign of ignorance that could be cured by more knowledge, or is it baked into the very fabric of existence? These are not small questions. These are perhaps the biggest questions anyone has ever asked about the nature of the universe. And in 1927, at the 5th Solvay Conference in Brussels, the battle lines were drawn. The 5th Solvay Conference of 1927 is one of the most remarkable gatherings in the history of science. The photograph from this conference is legendary. In one image you can see Albert Einstein, Niels Bohr, Max Planck, Werner Heisenberg, Erwin Schrödinger, Max Born, Paul Dirac, Louis de Broglie, Wolfgang Pauli, and many other luminaries. Of the 29 attendees, 17 would eventually win Nobel Prizes. It was perhaps the greatest concentration of scientific genius ever assembled in one room. At this conference, Born and Heisenberg presented a paper in which they made a stunning declaration. They declared that quantum mechanics is a closed theory, that its fundamental physical and mathematical assumptions are no longer susceptible to any modification. In other words, the theory is complete. There is nothing more to find. There are no hidden variables. The randomness is genuine. The uncertainty is real. This is how nature works, and we need to accept it. Einstein was horrified. He could not accept that the story was over, that physics had reached a fundamental, uncrossable barrier of ignorance. He began constructing thought experiments designed to show that the uncertainty principle could be violated, that you could, in principle, know both the position and velocity of a particle simultaneously with arbitrary precision. At the conference, Einstein proposed an ingenious thought experiment involving a beam of particles passing through a slit. The basic idea was that by carefully measuring the recoil of the screen through which the particle passes, you could determine which path the particle took without disturbing the interference pattern that proves its wave nature. If this worked, it would mean you could observe both the wave and particle nature of a quantum object simultaneously, which the Copenhagen interpretation said was impossible. Bohr responded with a brilliant counter-argument. He showed that the very act of measuring the screen's recoil with enough precision would introduce an uncertainty in the screen's position, and this uncertainty would wash out the interference pattern. The uncertainty principle was preserved. Einstein was not convinced, but he could not immediately find a flaw in Bohr's reasoning. He went away and worked on a new thought experiment, an even more clever one, which he presented at the 6th Solvay Conference in 1930. This time, Einstein came prepared with what he considered a devastating argument against the energy-time uncertainty relation. He proposed a device that has come to be known as Einstein's light box. Imagine a box filled with photons, with a hole in one wall covered by a shutter. The shutter is connected to a clock inside the box. At a precisely determined time, the shutter opens briefly and allows exactly one photon to escape. Now, Einstein said, weigh the box before and after the photon escapes. By his own famous equation E equals mc squared, the tiny decrease in mass tells you the exact energy of the escaped photon, and the clock tells you the exact time it escaped, so you know both the energy and the time precisely. This would violate the energy-time uncertainty relation. What happened next is one of the most dramatic moments in the history of physics. Leon Rosenfeld, who was present, later described the scene. He said it was a real shock for Bohr, who at first could not think of a solution. For the entire evening, Bohr was extremely agitated, passing from one scientist to another, trying to convince them that Einstein could not be right, that it would be the end of physics if he were. But Bohr could not find the flaw. Rosenfeld described the image of the two antagonists leaving the hall that night. Einstein walking tall and calm with a mildly ironic smile, Bohr trotting along beside him in a state of great excitement. But the next morning, Bohr had his answer, and it was devastating. Bohr turned Einstein's own theory of general relativity against him. He pointed out that when you add weight to rebalance the box after the photon escapes, the box moves slightly in the gravitational field. And according to general relativity, clocks at different heights in a gravitational field tick at different rates. This gravitational time dilation introduces an uncertainty in the time measurement that is exactly enough to preserve the energy-time uncertainty relation. Einstein's own theory of gravity saved the uncertainty principle. Einstein was stunned. He did not immediately find a response. But he was not defeated, not in his core belief. He just realized that direct frontal attacks on the uncertainty principle were not going to work. He needed a different strategy, and this is where the story takes its most important turn. Between 1930 and 1935, Einstein underwent a fundamental shift in his thinking. He stopped trying to prove the uncertainty principle wrong. He accepted that you cannot simultaneously measure the position and momentum of a particle with arbitrary precision. But he drew a crucial distinction. He said, "I accept that we cannot measure both at once. But I deny that this means the particle does not possess both values. Just because you cannot see both sides of a coin at the same time does not mean the coin does not have two sides." This distinction is absolutely critical and often misunderstood. Einstein was not denying quantum mechanics. He was not saying the equations were wrong. He was not saying the experimental predictions were incorrect. He was saying that the theory was incomplete, that there was a deeper level of reality that quantum mechanics was not capturing, a level where particles have definite properties, where randomness is replaced by certainty, where hidden variables determine everything with precision. Quantum mechanics, in Einstein's view, was like thermodynamics. It was a brilliant statistical description that captured the average behavior perfectly, but beneath it, there was a more fundamental deterministic theory waiting to be discovered. And in 1935, Einstein delivered what is widely considered the most powerful and beautiful argument of his entire career in quantum physics. It was not the work of a defeated man. It was the work of a genius at the height of his powers, constructing an argument of such logical precision and philosophical depth that it would reshape the foundations of physics. In May 1935, a paper appeared in the Physical Review with the title, "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" The authors were Albert Einstein, Boris Podolsky, and Nathan Rosen, and the argument it contained became known as the EPR Paradox. Interestingly, Einstein was not entirely happy with the way the paper turned out. It was primarily written by Podolsky, and Einstein later told Erwin Schrödinger that the essential thing was, so to speak, smothered by the formalism. But the core argument was pure Einstein, and it was extraordinary. Before laying out the argument, EPR established a criterion of reality, a seemingly undeniable principle that they would use as the foundation of their reasoning. The criterion was this: if, without in any way disturbing a system, we can predict with certainty the value of a physical quantity, then there exists an element of physical reality corresponding to that quantity. Think about what this means in simple terms. If you can predict with 100% certainty what you will find when you measure something, without doing anything to the system, then that property must have been real all along. It was not created by the measurement. It existed before you looked. This seems like the most common sense statement in the world. If you can guarantee what you will find in a sealed box without opening it, then whatever is in the box is real, regardless of whether you open it. It is not your opening that creates the contents. Now here is the thought experiment. Imagine two particles that interact with each other and then fly apart in opposite directions. Quantum mechanics describes them as being in an entangled state. The word entanglement, by the way, was coined by Erwin Schrödinger in the very same year, 1935, in response to the EPR paper. He called it not one, but the characteristic trait of quantum mechanics. So these two particles are entangled and flying apart. Let us call them particle A and particle B. Alice has particle A and Bob has particle B. They are now very far apart, perhaps on opposite sides of the Earth, perhaps on opposite sides of the galaxy. According to quantum mechanics, the particles are in a superposition, a combined state where neither particle has a definite value for properties like position or momentum until one of them is measured. Now here is the key. If Alice measures the position of particle A, she gets a definite result. And because of the entanglement, she can now predict with absolute certainty the position of particle B. Remember the EPR criterion of reality. If she can predict the position of particle B with certainty, without disturbing it in any way, then particle B must have had a definite position all along. It was real before she measured it. But wait. Alternatively, Alice could have chosen to measure the momentum of particle A instead. And because of entanglement, she could then predict with absolute certainty the momentum of particle B. So by the same reasoning, particle B must have had a definite momentum all along. Now comes the crucial step. Alice is very far away from Bob. Her measurement on particle A cannot physically disturb particle B, because no signal can travel faster than light. And Alice and Bob are far enough apart that even light could not have carried any influence from Alice's measurement to particle B in the time it takes. This is the assumption of locality, one of the most fundamental principles of physics, a direct consequence of Einstein's own special relativity. Since Alice's choice of what to measure on particle A cannot affect particle B, and since she could have chosen either measurement, particle B must simultaneously possess definite values for both position and momentum. It must have had a real position and a real momentum, existing independently, before any measurement was performed. But quantum mechanics says this is impossible. The Heisenberg uncertainty principle says that a particle cannot simultaneously have a definite position and a definite momentum. If the particle has a definite position, its momentum is fundamentally uncertain, and vice versa. These are not just limits on measurement. They are supposed to be fundamental features of reality. So EPR had constructed a logical argument that led to a contradiction. If you accept locality, which seems mandatory from special relativity, and if you accept the EPR criterion of reality, which seems like basic common sense, then you are forced to conclude that particles have definite values for properties that quantum mechanics says they cannot have. The conclusion that EPR drew was not that quantum mechanics is wrong, but that it is incomplete. There must be additional information, hidden variables, that quantum mechanics does not capture. The wave function gives you probabilities, but beneath those probabilities there is a definite, determined reality that the theory fails to describe. The EPR paper landed in the physics world like a bombshell. The New York Times ran a story with the headline, "Einstein Attacks Quantum Theory." This actually annoyed Einstein, who had not authorized the press coverage and felt that scientific matters should be discussed in scientific forums, not newspapers. But the damage, or rather the impact, was done. Everyone in physics was talking about it. Niels Bohr was deeply shaken. He spent 6 weeks crafting his response, which he published in the same journal with the same title. Bohr's counter-argument was subtle and, to many, somewhat difficult to follow. He argued that EPR's reasoning contained an ambiguity regarding the meaning of the phrase without in any way disturbing a system. Bohr's point was that even though Alice's measurement does not send any physical signal to particle B, her choice of what to measure changes the entire experimental context. The position measuring setup and the momentum measuring setup are, in Bohr's view, two completely different physical situations. You cannot combine predictions from one situation with predictions from the other. The EPR criterion of reality, Bohr argued, is not as innocent as it seems when applied to quantum systems. Bohr introduced his principle of complementarity to address this. He argued that position and momentum are complementary properties. They can only be defined within mutually exclusive experimental arrangements. Asking what the momentum of a particle is while measuring its position is, in Bohr's framework, a meaningless question, not because we cannot answer it, but because the question itself has no content outside of a specific experimental context. Many physicists found Bohr's response convincing, but many others did not. Abraham Peiss, who knew both men well, described the situation as follows. Bohr's arguments were too subtle for most physicists to fully grasp. But they accepted his conclusion because quantum mechanics worked so extraordinarily well in practice. Einstein was not among those who accepted it. He considered Bohr's argument to be essentially philosophical hand-waving that avoided the real issue. And here, for nearly 30 years, the debate stalled. Most physicists adopted what came to be informally known as the shut up and calculate attitude. Quantum mechanics makes incredibly precise predictions. It explains the behavior of atoms, molecules, semiconductors, lasers, and a vast range of other phenomena. The philosophical questions about what it all means, about whether particles really lack definite properties until observed, about whether hidden variables exist, these questions were pushed aside as impractical and possibly meaningless. But Einstein never stopped thinking about it. He continued to believe, until the day he died in 1955, that quantum mechanics was an incomplete theory, that there must be a deeper, deterministic level of reality described by hidden variables. And most of the physics community believed he was wrong. But the story does not end there. Not by a long shot. Because during those quiet decades, while most physicists were ignoring the question, some remarkable things happened that would eventually blow the entire debate wide open. The first of these was a proof, or rather what was believed to be a proof, that hidden variables are mathematically impossible. In 1932, the great mathematician John von Neumann published his book, Mathematical Foundations of Quantum Mechanics. In it, he included what he presented as a rigorous mathematical proof that no hidden variable theory could reproduce the predictions of quantum mechanics. Von Neumann was perhaps the most formidable mathematical mind of the 20th century. He made fundamental contributions to set theory, functional analysis, quantum mechanics, computer science, game theory, and nuclear weapons design. When von Neumann said something was mathematically proven, people believed him. And so, for decades, physicists cited von Neumann's proof as the final word on hidden variables. The question is not just physically settled, they said, it is mathematically impossible. Hidden variables cannot exist. End of story. But there was a problem with von Neumann's proof, a subtle but fatal flaw. And the person who first identified it was a young German mathematician and philosopher named Greta Hermann. In 1935, the very same year as the EPR paper, Hermann published an analysis of von Neumann's proof in which she identified a critical error. Von Neumann had assumed that a certain mathematical property, the linearity of expectation values, must hold for hidden variables, just as it holds for quantum mechanical observables. But this is a completely unjustified assumption. There is no reason why the hidden variables, which are by definition different from quantum observables, should satisfy this same mathematical relationship. Hermann's critique was correct and devastating, but it was almost completely ignored. She published it in a relatively obscure philosophical journal, the Abhandlungen der physischen Schule, and in the intellectual climate of 1935 Germany. A woman publishing in a philosophy journal was not likely to attract the attention of the physics establishment. Her work languished in obscurity for decades. Think about the magnitude of this missed opportunity. If Hermann's critique had been recognized in 1935, the hidden variables question would have been reopened 30 years earlier. The entire trajectory of 20th century physics might have been different. Bell's theorem might have been discovered in the 1940s instead of the 1960s. The experimental tests might have been performed decades earlier. The quantum information revolution might have begun before the computer revolution. But history does not work that way. The insight was buried, and the false belief that hidden variables were mathematically impossible persisted. It was not until 1952 that a physicist demonstrated conclusively that von Neumann was wrong, not by finding the flaw in the proof as Hermann had, but by actually constructing a working hidden variable theory. That physicist was David Bohm. David Bohm was an American physicist who had studied under J. Robert Oppenheimer at Berkeley. He was brilliant, unconventional, and deeply interested in the philosophical foundations of physics. In 1952, Bohm published 2 papers with the title A Suggested Interpretation of the Quantum Theory in Terms of Hidden Variables. In these papers, he presented a fully worked out, mathematically consistent hidden variable theory that reproduced all the predictions of standard quantum mechanics. Bohm's theory, which is now known as the de Broglie-Bohm theory or pilot wave theory, was actually a rediscovery and extension of an idea that Louis de Broglie had proposed at the 5th Solvay Conference in 1927. De Broglie had suggested that every particle is accompanied by a wave, a pilot wave, that guides its motion through space. The particle itself always has a definite position and follows a definite trajectory. But its motion is guided by the pilot wave, which obeys Schrödinger's equation. De Broglie had been discouraged from pursuing this idea after receiving criticism at the 1927 conference, particularly from Wolfgang Pauli, and had abandoned it. Bohm brought it back to life in a much more developed and rigorous form. In Bohm's theory, every particle always has a definite position. There is no superposition for the particle itself, although the pilot wave exists in a superposition. When you perform a measurement, the result is determined by the actual position of the particle, which has been guided by the pilot wave into a specific location. The apparent randomness of quantum mechanics arises because we do not know the exact initial position of the particle. If we knew it, we could predict every measurement outcome with perfect certainty. Let me give you a concrete example. Consider the famous double-slit experiment. In standard quantum mechanics, a single particle approaches a barrier with 2 slits, and somehow an interference pattern builds up on the screen behind the barrier, as if the particle went through both slits simultaneously. The standard interpretation says the particle did not go through one slit or the other, it went through both, or perhaps neither. The question of which slit it went through is meaningless. In Bohm's theory, the picture is completely different. The particle goes through exactly one slit. It always has a definite position. But the pilot wave goes through both slits, and the interference between the 2 parts of the pilot wave on the other side of the barrier guides the particle to a position on the screen that, when many particles are sent through, produces the observed interference pattern. The particle is always a particle. The wave is a real, physical wave that guides it. There is no mystery, no collapse, no superposition of the particle, just a particle being pushed around by a wave. This was exactly the kind of theory Einstein had dreamed of. Particles have definite properties at all times. The randomness is explained by ignorance of initial conditions, not by fundamental indeterminacy. The universe is deterministic. But there was a catch. A big, unavoidable catch. Bohm's theory is non-local. The pilot wave is a function defined not in our ordinary three-dimensional space, but in configuration space, a vast abstract mathematical space that has three dimensions for every particle in the universe. When Alice measures particle A in the EPR experiment, the pilot wave throughout this entire configuration space changes instantaneously. And this instantaneous change affects the motion of particle B, no matter how far away it is. The theory has exactly the kind of spooky action at a distance that Einstein found so objectionable. Einstein was not impressed with Bohm's theory. He found it too artificial, too contrived. It was technically a hidden variable theory, and it was deterministic, but it sacrificed locality, which for Einstein was just as fundamental. Pauli and Heisenberg dismissed it. Most physicists ignored it. But there was one person who did not ignore it. A young physicist at CERN named John Stuart Bell was deeply intrigued. When Bell read Bohm's papers, he later recalled he saw the impossible done. Von Neumann had supposedly proved that hidden variables were impossible. And here was a working hidden variable theory. Something was clearly wrong with von Neumann's proof. Bell investigated and independently discovered the flaw that Gret Hermann had identified 2 decades earlier. Von Neumann's supposedly airtight proof contained an unjustified assumption. Hidden variables were not impossible after all. But Bell did not stop there. He asked the question that would change physics forever. He asked, can we distinguish experimentally between quantum mechanics and local hidden variable theories? This question had never been clearly formulated before. Most people assumed that since Bohm's theory made the same predictions as quantum mechanics, hidden variable theories could never be tested. But Bell realized something crucial. Bohm's theory is non-local. What about local hidden variable theories? Could a theory where particles have predetermined properties and where no influence travels faster than light also reproduce all the predictions of quantum mechanics? Bell worked on this question quietly, almost secretly, because it was considered an unfashionable topic at CERN. His colleagues were focused on particle physics, not on philosophical questions about the foundations of quantum mechanics. Bell once said that he worked on his theorem during weekends and evenings, describing it as his hobby. In 1964, Bell published a short paper, only 6 pages long, titled On the Einstein-Podolsky-Rosen Paradox. In this paper, he proved what is now known as Bell's theorem, and it is no exaggeration to say that it is one of the most important results in the entire history of physics. To understand Bell's theorem, let me build it up carefully, because this is the absolute core of our story. And I want you to understand it not just in terms of the math, but in terms of the deep meaning. Let us start with an analogy. Imagine a factory that produces pairs of special coins. These are not ordinary coins. Each coin has 3 sides. Let us call them side A, side B, and side C. Actually, that is a bit hard to visualize, so let me change the analogy. Imagine instead that each coin has 3 buttons on it, labeled 1, 2, and 3. When you press one of the buttons, the coin either flashes red or green. Part 2, the factory, sends 1 coin to Alice and 1 coin to Bob. Alice and Bob are very far apart in different cities. They each randomly choose one of the 3 buttons and press it, and they record whether their coin flashed red or green. They repeat this many times, with many pairs of coins, always choosing their buttons randomly and independently. Now, here is the key question. What are the correlations between Alice and Bob's results? Let us first consider the hidden variables scenario. The factory owner is clever. Before sending out each pair of coins, he programs instructions into them. Each coin has a preset instruction for each button. For example, coin A might be programmed as button 1 gives red, button 2 gives green, button 3 gives red. And coin B, being the partner of coin A, might be programmed to always give the opposite result. So coin B would be button 1 gives green, button 2 gives red, button 3 gives green. The factory owner can choose whatever instructions he wants for each pair, and the instructions can be different for each pair. But there is one rule. Once the coins leave the factory, they cannot communicate with each other. No signals, no messages, no coordination. Whatever they do when a button is pressed must be determined entirely by the instructions they carry with them. This is the analogy for local hidden variables. The factory is the source of entangled particles. The coins are the particles. The buttons are the different measurement choices that Alice and Bob can make. The instructions are the hidden variables. And the rule against communication is the assumption of locality. Now, Bell's brilliant insight was this. No matter what instructions the factory owner programs into the coins, there is a mathematical limit on how correlated Alice and Bob's results can be. If they press the same button, the results are always perfectly correlated, in this case, perfectly anti-correlated. But when they press different buttons, the correlations are constrained. Here is a simplified version of the argument. Consider a specific pair of coins. The hidden instructions determine what happens for each button. Let us say the instruction for coin A is to flash red for button 1, red for button 2, and green for button 3. Let us write this as RRG. The partner coin B always gives the opposite, so it is GGR. Now, if Alice presses button 1 and Bob presses button 2, Alice gets red and Bob gets green. They get different colors. If Alice presses button 1 and Bob presses button 3, Alice gets red and Bob gets red. They get the same color. If Alice presses button 2 and Bob presses button 3, Alice gets red and Bob gets red. Same color again. For this particular instruction set, when they press different buttons, they get the same color 2/3 of the time and different colors 1/3 of the time. You can work through all possible instruction sets, and the math shows that for any local hidden variable theory, when Alice and Bob press different buttons, they must get the same result at least 1/3 of the time. This is a version of Bell's inequality. It is a mathematical constraint that any local hidden variable theory must satisfy. Now comes the astonishing part. Quantum mechanics predicts something different. For the right choice of measurement angles, analogous to our button choices, quantum mechanics predicts that when Alice and Bob make different measurements on entangled particles, they will get the same result only 1/4 of the time, not 1/3. 1/4 is less than 1/3. The quantum mechanical prediction violates Bell's inequality. This is not a small technical distinction. This is a fundamental divide. If local hidden variables are right, the correlations cannot go below 1/3. If quantum mechanics is right, the correlations go to 1/4. These are different numbers, and you can check which one nature actually gives you by doing experiments. Let me also explain the more general and commonly used form of the inequality, known as the Kish inequality, named after John Clauser, Michael Horn, Abner Shimoni, and Richard Holt, who derived it in 1969. In this formulation, you define a quantity called S that combines the correlations between Alice and Bob's measurements at 4 different angle pairs. For any local hidden variable theory, this quantity S must satisfy the constraint that S is less than or equal to 2. But quantum mechanics predicts that S can be as large as 2 times the square root of 2, which is approximately 2.828. That is a 40% violation of the limit. This difference between 2 and 2.828 is the battlefield where Einstein's dream would be tested. It is a clear, precise, numerical prediction. If you measure S and get a number less than or equal to 2, local hidden variables win. If you measure S and get a number greater than 2, quantum mechanics wins and local hidden variables lose. For the first time since the EPR paper was published in 1935, the debate between Einstein and Bohr was no longer a matter of philosophical taste. It was a matter of experimental fact. And experiments could be done. But before we get to the experiments, I want you to really feel the depth of what Bell had achieved. For 30 years, the greatest minds in physics had argued about whether quantum mechanics was complete or whether hidden variables existed. The debate had been philosophical, based on thought experiments and logical arguments. Nobody knew how to settle it empirically. And then this quiet Irishman working at CERN in his spare time figured out a way to ask nature directly. He found a question that local hidden variables and quantum mechanics answer differently. He turned philosophy into physics. Bell himself was clearly moved by the implications of his result. He was, by most accounts, sympathetic to Einstein's position. He liked the idea of a deterministic universe. He liked Bohm's theory. He found the Copenhagen interpretation unsatisfying. And yet his own theorem showed that if you want determinism, if you want hidden variables, you have to give up locality. You have to accept spooky action at a distance. There is no way to have both determinism and locality. Now, Bell's theorem is a mathematical proof. It does not care about experiments. It says, if nature satisfies certain assumptions, then certain constraints follow. The experiments are needed to check whether nature actually satisfies those constraints. And the experiments began almost immediately. The first serious experimental test of Bell's inequality was performed in 1972 by John Closer and Stuart Friedman at the University of California, Berkeley. Closer had been thinking about Bell's theorem since he first encountered it as a graduate student, and he was determined to test it. Closer and Friedman used pairs of entangled photons produced by excited calcium atoms. They measured the polarization of each photon at different angles and computed the correlations. Their experiment was not easy. The technology of the early 1970s was not designed for this kind of precision measurement. But they got a result, and the result was clear. Bell's inequality was violated. The correlations between the entangled photons exceeded the limit set by local hidden variables. The data matched the quantum mechanical prediction. Einstein's local hidden variables took a direct hit. But Closer and Friedman were careful scientists, and they knew their experiment had limitations. There were loopholes, potential escape routes that a defender of local hidden variables could exploit to argue that the result was not conclusive. The most important loophole was the locality loophole. In Closer and Friedman's experiment, the two detectors were close enough together that in principle, information could have traveled from one to the other at the speed of light during the time of the measurement. A determined hidden variable theorist could argue that maybe the first detector somehow sent a signal to the second detector, telling it what result had been obtained, and the second detector adjusted its behavior accordingly. This seems far-fetched, but science demands that you close loopholes, not just dismiss them. The second loophole was the detection loophole, also called the fair sampling loophole. Photon detectors are not perfect. They miss many of the photons that are sent to them. In Clauser and Friedman's experiment, only a small fraction of the photon pairs were actually detected. A hidden variable theorist could argue that perhaps the detected photons are not a representative sample. Maybe the photons that were missed are the ones that would have obeyed Bell's inequality, and the experiment is seeing only a biased subset. These loopholes are not just nitpicking. They represent genuine logical gaps in the argument. To conclusively rule out local hidden variables, you need to close all the major loopholes simultaneously. And in 1972, nobody could do that. Enter Alain Aspect. Aspect was a young French physicist who had been deeply inspired by Bell's work. In the early 1980s, he designed and carried out a series of experiments at the University of Paris South in Orsay that would become legendary in the history of physics. Aspect's key innovation was to address the locality loophole head-on. He used an ingenious technique in which the measurement settings were changed while the photons were already in flight. Here is how it worked. Instead of fixing the angle of the polarization measurement before the experiment, Aspect used fast optical switches that could redirect each photon to one of two different analyzers set at different angles. The switching was done so rapidly that it occurred after the photons had left the source, but before they reached the detectors. This meant that the choice of which measurement to perform on each photon was made when the photons were already traveling, and there was no time for a signal traveling at the speed of light to carry information from one detector to the other. This was brilliant. If a hidden variable theorist wanted to invoke communication between the detectors, they would now have to propose faster-than-light communication, which would violate the most fundamental principle of special relativity. The locality loophole was effectively closed. Aspect also used a dramatically improved source of entangled photons. He used a 2-photon laser excitation of calcium atoms, which produced entangled photon pairs at a much higher rate and with much higher quality than previous experiments. This meant more data, better statistics, and a more convincing result. The result was stunning. Aspect's experiments violated Bell's inequality by up to 5 standard deviations. In statistical terms, this means that if local hidden variables were true, the probability of seeing a result this extreme by chance is less than 1 in a million. The quantum mechanical prediction was confirmed with overwhelming precision. When Aspect presented his results, the physics world took notice. This was not a marginal effect, not a questionable result that could be explained away. This was a clear, decisive violation of Bell's inequality, obtained with an experimental design specifically crafted to close the most important loophole. But the detection loophole remained open. Aspect's detectors still missed a significant fraction of the photon pairs, and so the door to local hidden variables, while now hanging by a single hinge, was not yet fully closed. Over the next 3 decades, a series of increasingly sophisticated experiments chipped away at the remaining loopholes. Anton Zeilinger and his group in Austria made enormous advances. They demonstrated quantum entanglement over increasingly long distances, eventually performing experiments where entangled photons were separated by hundreds of kilometers. They pioneered quantum teleportation experiments, showing that quantum states could be transferred from one particle to another using entanglement and classical communication. They developed better sources of entangled photons and more efficient detectors. But the Holy Grail, the loophole-free Bell test, remained elusive. To close all loopholes simultaneously, you needed high-efficiency detectors that do not miss too many particles, You needed the measurement settings to be chosen and implemented fast enough to close the locality loophole. And you needed truly random choices of measurement settings to close what is called the freedom of choice loophole. In 2015, the Holy Grail was finally achieved. A team led by Ronald Hansen at the Delft University of Technology in the Netherlands performed what is widely considered the first truly loophole-free Bell test. Their experiment used a different approach from the photon experiments. Instead of photons, they used the spins of individual electrons trapped in diamond crystals. 2 such crystals were placed 1.3 kilometers apart. Through a clever protocol involving both the electron spins and photons, they created entangled pairs of electrons at this distance. The beauty of their approach was that the electrons were trapped in solid crystals, so there was no detection loophole. Every entangled pair was detected. The measurement settings were chosen by quantum random number generators, so there was no freedom of choice loophole. And the 1.3 kilometer separation, combined with the fast switching, closed the locality loophole. The result, published in Nature in October 2015, was unambiguous. Bell's inequality was violated. The statistics were strong enough to rule out local hidden variables with high confidence. In the very same year, 2 other groups independently performed loophole-free Bell tests using different techniques. A team led by Marissa Giustina in Anton Zeilinger's group in Vienna used entangled photons with high-efficiency detectors, and a team at the National Institute of Standards and Technology in the United States performed yet another loophole-free test. All 3 experiments agreed. Bell's inequality was violated. Local hidden variables are not compatible with reality. The scientific community recognized the monumental significance of this work. In 2022, the Nobel Prize in Physics was awarded jointly to John Clauser, Alain Aspect, and Anton Zeilinger, with a citation for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. This was the official seal on one of the longest and most important debates in the history of science. From the EPR paper in 1935 to the Nobel Prize in 2022, it had taken 87 years to fully resolve the question that Einstein had raised. And the resolution was clear. Local hidden variables do not work. You cannot explain the behavior of entangled particles by assuming that each particle carries a predetermined set of instructions and that no influence travels faster than light. The correlations between entangled particles are stronger than any local hidden variable theory can produce. Nature violates Bell's inequality. Einstein's dream of a locally deterministic universe is dead. But wait, is that the whole story? Is Einstein simply wrong, and is the Copenhagen interpretation simply right? The answer, as I promised at the beginning, is far more nuanced and far more interesting than a simple yes or no. Let us be very precise about what has been ruled out and what has not. What has been ruled out is the conjunction of 3 assumptions. The assumption of locality, that no influence travels faster than light. The assumption of realism, that particles have definite properties independent of measurement. And the assumption of free choice, that experimenters can freely choose what to measure. Bell's theorem says that you cannot have all 3. Nature forces you to give up at least one. Most physicists take the experiments to rule out local realism, meaning the combination of locality and realism. But this still leaves open the question of which one to give up, and there are brilliant physicists on every side of this question. If you give up realism but keep locality, you get something like the Copenhagen interpretation. Particles do not have definite properties until measured. The wave function is a complete description. Randomness is fundamental. This is the most popular interpretation among working physicists, largely because it is the most pragmatic and does not require any additional mathematical structure beyond standard quantum mechanics. If you give up locality but keep realism, you get something like Bohm's pilot wave theory. Particles always have definite positions. The randomness is apparent, not fundamental. But the pilot wave connects all particles non-locally, acting instantaneously across the universe. This interpretation has a small but dedicated following among physicists and philosophers. It is mathematically consistent, makes the same predictions as standard quantum mechanics, and provides a clear, deterministic picture of reality. But the non-locality is hard to swallow, especially for anyone trained in relativistic physics. If you give up free choice, you get superdeterminism. This is the idea that the experimenter's choices of measurement settings are not truly free, but are predetermined by the same underlying cause that also determines the particle's behavior. In this view, the correlations between the particles and the measurement choices are not a sign of non-locality, but a sign of a common cause stretching back to the beginning of the universe. Superdeterminism is perhaps the most controversial option. Most physicists find it distasteful because it seems to undermine the very foundation of experimental science. If your choices as an experimenter are not free, if the universe has conspired to determine what you measure and what you find, then in what sense can any experiment be said to test anything? The physicist John Bell acknowledged that superdeterminism is a logical possibility, but called it conspiratorial, and said he would not even consider it. However, a small number of respectable physicists, including Nobel laureate Gerard Hooft, have argued that superdeterminism deserves more serious consideration. After all, in a deterministic universe, every choice is determined by prior causes. The question is whether the correlations required for superdeterminism are plausible, or whether they require a cosmic fine-tuning of incredible implausibility. But there are also other possibilities, other interpretations that try to make sense of quantum mechanics without hidden variables and without giving up on a coherent picture of reality. The many worlds interpretation, first proposed by Hugh Everett in 1957, takes a radical approach. It says that every possible outcome of every quantum measurement actually occurs, but in different branches of a constantly splitting universe. When Alice measures the spin of an entangled particle and gets up, there is another branch of the universe where she got down. Both outcomes are real. Both Alices are real. The universe is not random, it is deterministic in the sense that the universal wave function evolves deterministically according to the Schrödinger equation. There is no collapse, there is no randomness, there is just branching. The many worlds interpretation is gaining popularity among physicists, particularly among those working in quantum computing and quantum information. It has the virtue of simplicity in the sense that it adds nothing to the mathematics of quantum mechanics. The wave function is real, it evolves deterministically, and that is the whole story. The price you pay is accepting that there are an incomprehensibly vast number of parallel universes, all equally real, splitting off from each other every time a quantum event occurs. Another interpretation that has gained attention in recent years is cubism, short for quantum Bayesianism. Cubism takes the radical position that the wave function does not describe objective reality at all. Instead, it represents an individual agent's beliefs about what they will experience upon making a measurement. Quantum mechanics, in this view, is not a theory about the world. It is a theory about what any given person should expect. The probabilities in quantum mechanics are not objective frequencies. They are subjective degrees of belief, updated in light of experience. Cubism neatly avoids the measurement problem and the difficulties with non-locality. But it does so at the cost of seemingly giving up on the idea that physics describes an objective reality independent of observers. Whether this is a feature or a bug depends on your philosophical inclinations. Then there is relational quantum mechanics, proposed by Carlo Rovelli, which says that quantum states are not absolute, but relative to a particular observer. Different observers may have different, equally valid descriptions of the same system. There is no view from nowhere, no God's eye perspective. Reality is a network of relations, not a collection of absolute facts. And there are objective collapse theories, such as the GRU theory named after Girardi, Rimini, and Weber, which modify the Schrödinger equation by adding a tiny random collapse mechanism. In these theories, the wave function is a real physical entity that usually evolves according to the Schrödinger equation, but occasionally, spontaneously, randomly collapses. The rate of collapse is negligible for individual particles, but becomes significant for large, macroscopic objects, which is why cats are never observed in superpositions of alive and dead. These theories actually make slightly different predictions from standard quantum mechanics, which means they are in principle testable, and experiments to test them are being designed and carried out. The point of going through all these interpretations is not to tell you which one is right, because frankly, nobody knows. The point is to show you that the hidden variables debate, far from being a settled historical curiosity, opens up onto some of the deepest and most active areas of modern physics and philosophy. And now, I want to tell you about something truly remarkable. Something that suggests Einstein might get a kind of cosmic vindication in the most unexpected way. In 2013, two theoretical physicists, Juan Maldacena and Leonard Susskind, proposed a conjecture that sent shockwaves through the physics community. They proposed that ER equals EPR. Let me explain what this means. ER refers to Einstein-Rosen bridges, better known as wormholes. In 1935, the very same year as the EPR paper, Einstein and Rosen published another paper in which they showed that general relativity allows for the existence of bridge-like connections between distant points in space. These are tunnels through the fabric of space-time, shortcuts from one location to another. EPR, of course, refers to the Einstein-Podolsky-Rosen entanglement that we have been discussing throughout this video. The ER equals EPR conjecture says that these two phenomena, wormholes and entanglement, are actually the same thing. Every pair of entangled particles is connected by a tiny, microscopic wormhole through space-time. The spooky action at a distance that Einstein found so objectionable is not action at a distance at all. It is action through a shortcut in the geometry of space-time. If this conjecture is correct, and it is taken very seriously by many leading theoretical physicists, then the entanglement that seems so mysterious from the quantum mechanical perspective has a beautiful, geometric explanation in terms of general relativity. The two great pillars of 20th century physics, quantum mechanics and general relativity, are connected at their deepest level. And here is the breathtaking irony. Both of these concepts, wormholes and entanglement, were introduced in papers by Einstein himself, both published in 1935. Einstein spent the last 30 years of his life searching for a unified theory that would connect quantum mechanics and gravity, and the answer may have been hidden in his own work all along. The two papers he published in 1935, the EPR paper and the Einstein-Rosen paper, may be two sides of the same coin. ER equals EPR might be the deep unification that Einstein was searching for, emerging from his own discoveries in a way he never imagined. We do not yet know if ER equals EPR is correct. It is a conjecture, not a proven theorem, and a great deal of work remains to be done. But the fact that such a connection is even being seriously considered by the physics community shows that Einstein's questions, his objections, his stubborn refusal to accept the Copenhagen interpretation without deeper understanding, were not the misguided efforts of an aging physicist out of touch with modern science. They were the prescient insights of a thinker whose vision extended far beyond what anyone else could see. Let me also talk about another aspect of this story that often gets overlooked, which is the extraordinary technological revolution that has sprung from these seemingly abstract philosophical debates. Quantum entanglement. The phenomenon that Einstein called spooky and that he saw as a problem to be solved is now the foundation of entirely new fields of technology. Quantum computing, which promises to solve certain problems that are completely beyond the reach of any classical computer, relies fundamentally on entanglement. A quantum computer's power comes from the ability to put multiple quantum bits, or qubits, into entangled states that can explore many possible solutions simultaneously. Quantum cryptography, which promises perfectly secure communication, also relies on the peculiar properties of quantum measurement that Einstein found so troubling. In quantum key distribution, two parties can create a shared secret key that is guaranteed to be secure by the laws of physics. Any attempt to eavesdrop necessarily disturbs the quantum states being used, which alerts the communicating parties to the presence of the eavesdropper. Bell's inequality is actually used as a practical security test in some quantum cryptography protocols. If the correlations between the two parties' measurements violate Bell's inequality, they can be sure that their quantum channel is secure. Quantum teleportation, the transfer of a quantum state from one particle to another using entanglement and classical communication, has been demonstrated over satellite links spanning thousands of kilometers. This technology, which seems straight out of science fiction, is directly traceable to the EPR paper of 1935. The very phenomenon that Einstein saw as evidence that quantum mechanics was incomplete is now being used to build a quantum internet. And the story keeps unfolding. There is still no universally accepted interpretation of quantum mechanics. The measurement problem remains unsolved. Nobody has yet successfully unified quantum mechanics with general relativity into a theory of quantum gravity. Many physicists believe that when we finally achieve this unification, our understanding of entanglement, measurement, and the nature of reality will be fundamentally transformed. Some researchers are exploring whether space-time itself might be emergent from quantum entanglement. The idea, inspired partly by the ER equals EPR conjecture, is that the smooth, continuous space-time described by general relativity is actually woven together from quantum entanglement between fundamental degrees of freedom. If this is correct, then entanglement is not just a strange property of quantum particles. It is the glue that holds the universe together. The fabric of space-time is knitted from quantum correlations. Others are exploring whether the Born rule, the rule that relates the wave function to probabilities, can be derived from deeper principles rather than simply postulated. If it can, it would provide a deeper understanding of why quantum mechanics has the probabilistic structure it does, and it might shed light on the hidden variables question from an entirely new angle. And still others are designing experiments to test the predictions of different interpretations of quantum mechanics. While all mainstream interpretations make the same predictions for currently achievable experiments, Some of them make slightly different predictions for extreme situations, such as very large quantum superpositions or situations involving gravity. As technology advances and allows us to create and control larger quantum systems, we may be able to actually distinguish between the interpretations experimentally, which would be an achievement of the highest order. Let me now bring us back to the central question of this video. The hidden variables theory that Einstein believed was true. What have we learned? We have learned that Einstein's belief in hidden variables was not a sign of confusion or stubbornness. It was rooted in a deep and coherent philosophical vision of what a physical theory should be. Einstein believed that physics should describe an objective reality that exists independently of observation. He believed that the universe should be deterministic, with every event having a definite cause. And he believed in locality, the principle that physical influences cannot travel faster than light. These three beliefs, realism, determinism, and locality, together form what is called local realism, and they are the philosophical foundation of hidden variable theories. If local realism is correct, then the apparent randomness of quantum mechanics must be explained by hidden variables, additional information that quantum mechanics does not capture. Just as the apparent randomness of a coin toss is explained by the physical variables of the throw that we do not bother to measure. Einstein developed this position through a series of increasingly sophisticated arguments, culminating in the EPR paper of 1935, which remains one of the most cited and most discussed papers in the history of physics. The EPR argument showed that if you accept locality and realism, then quantum mechanics must be incomplete. For nearly 30 years, this was treated as a philosophical question, incapable of experimental resolution. But then John Bell discovered that local hidden variable theories and quantum mechanics actually make different predictions for certain experiments involving entangled particles. Bell's inequality provided a clear, quantitative boundary. If the correlations between entangled particles stay within this boundary, local hidden variables are consistent with the data. If the correlations exceed this boundary, local hidden variables are ruled out. The experiments from Clauser and Friedman in 1972 through Aspect in 1982 to the loophole-free tests of 2015 have all given the same answer. Bell's inequality is violated. The correlations between entangled particles are stronger than any local hidden variable theory can produce. Nature has spoken, and it has spoken clearly. Local hidden variables are ruled out. Einstein was wrong about local hidden variables. But he was not simply wrong. He was wrong in a way that was incredibly productive and illuminating. His questions led directly to Bell's theorem, which led to the experiments, which led to the 2022 Nobel Prize, which led to the quantum information revolution that is transforming technology today. Being wrong in the right way, asking the right questions even if you do not like the answers, is sometimes more valuable than being right. And there are aspects of Einstein's vision that may yet prove correct in ways nobody expected. The ER equals EPR conjecture suggests that entanglement and wormholes may be the same phenomenon, which would mean that the non-locality of quantum mechanics has a perfectly geometric, perfectly rational explanation in terms of the structure of spacetime itself. Bohm's pilot wave theory shows that deterministic hidden variables are possible if you are willing to accept non-locality. And the many worlds interpretation shows that the universe can be deterministic and realistic without hidden variables, if you are willing to accept a wildly expanding ensemble of parallel worlds. The deepest lesson of this entire story, the one that I hope you will carry with you, is that the universe is stranger and more wonderful than any of us can imagine. And that the right response to this strangeness is not to turn away from it, but to lean in, to ask questions, to challenge assumptions, and to follow the evidence wherever it leads. Einstein followed the evidence of his own extraordinary intuition. Bohr followed the evidence of the mathematical formalism. Bell followed the evidence of both and found a way to let nature itself decide. And nature decided, not for Einstein, not for Bohr, but for something stranger and more beautiful than either of them had envisioned. There is a beautiful symmetry to this story. It begins with Einstein helping to create quantum mechanics and then spending the rest of his life questioning it. It passes through decades of philosophical debate that most physicists dismissed as meaningless. It reaches its climax with Bell's theorem, a result that emerged from the unfashionable hobby of a quiet physicist at CERN. And it is resolved by experiments that not only answer one of the deepest questions in physics, but also open the door to revolutionary new technologies. The hidden variables that Einstein believed in turned out not to be hidden in the particles. But the questions he asked about those hidden variables turned out to be hidden keys that unlocked some of the deepest secrets of the universe. In science, the questions are sometimes more important than the answers. And Einstein asked the best questions anyone has ever asked. There is one more thing I want to say before we end, and it is about the nature of scientific courage. Einstein took a position that was unpopular. He stood against the consensus of the physics community for 30 years. He was mocked and dismissed by many of his colleagues. He was told he was out of touch, that he was clinging to outdated ideas, that he was wasting his time. And in the specific technical sense of local hidden variables, his colleagues were right. But in the broader sense of demanding deep understanding, of refusing to accept a theory's success as a substitute for comprehension of what it means, Einstein was practicing the highest form of science. He was insisting that physics should not just predict, but should explain. He was insisting that the universe should make sense. And here is the thing. The universe does make sense. It just makes sense in a way that is radically different from what Einstein expected. It makes sense in terms of entanglement, non-locality, and correlations that cannot be explained by any local mechanism. It makes sense in terms of a reality that is, at its deepest level, not a collection of independent objects with fixed properties, but a web of relationships and correlations that extend across space-time in ways that our classical intuitions never prepared us for. This is not a defeat for rational understanding. This is a triumph of rational understanding. We used reason, logic, and experiment to discover that the universe is far stranger than we imagined. And the journey from Einstein's God does not play dice to the loophole-free Bell tests of 2015, and the Nobel Prize of 2022 is one of the greatest intellectual adventures in human history. Now let me take you through some of the finer details that often get overlooked but are crucial for a complete understanding of this story. One of the most important theorems in the hidden variables debate, after Bell's theorem itself, is the Kochen-Specker theorem, proved in 1967 by Simon Kochen and Ernst Specker. This theorem addresses a different aspect of the hidden variables question. While Bell's theorem is about locality, the Kochen-Specker theorem is about what physicists call contextuality. To understand contextuality, imagine that a particle has some property, let us call it its color, and you want to measure it. In classical physics, the color is a fixed property of the particle, and it does not matter how you measure it. You can measure it with one instrument or another, and you will always get the same answer, because the color is a property of the particle, not of the measurement. The Kochen-Specker theorem proves that in quantum mechanics, This is not possible. If you try to assign definite values to all measurable properties of a quantum system simultaneously, you run into a mathematical contradiction. Not because of randomness, and not because of non-locality, but because the properties are contextual. The value you get for a measurement depends on what other measurements you perform alongside it. The color of the particle, so to speak, depends on what other questions you are asking at the same time. This means that any hidden variable theory that reproduces the predictions of quantum mechanics must be contextual. The hidden variables cannot simply assign fixed values to all properties. They must also keep track of the measurement context. Bohm's pilot wave theory is contextual in exactly this way, which is why it survives the Cauchy-Specker theorem.